Hello, good morning, and welcome back to the good stuff that we have been doing. Today in this video, we're going to try to find this definite integral from 0 to 1 of x, 1 minus x divided by sine pi x dx, and it says the answer is 7 over pi cubed zeta of 3, where zeta of s is the sum as n runs from 1 to infinity of 1 over n to the s. So for example, zeta of 2 is the sum as n runs from 1 to infinity of 1 over n to the second power, and this is known to equal pi squared over 6, proven by Euler, known as the Bessel problem. Okay, so now we're going to look at this beautiful integral with us today, and let's see, how do we handle this? Well, this is perfectly set up for integration by parts, and the reason for this is because notice that x and 1 minus x, this product, they both vanish when x is 0 and when x equals to 1. Point being that if you do integration by parts, you only need to worry about the denominator. So that is why I say this problem is perfectly set up for integration by part. But we can't just do integration by part yet. Let's simplify things. First, take t to be pi x. Now, obviously, dt over pi would be dx. Then you would, when x is 0, t will be 0. But when x is 1, t will be pi. So you would have the integral from 0 to pi of x will be t over pi, of course, t over pi times 1 minus t over pi, all divided by sine t times what? You would have dt over pi. So now you can factor out 1 over pi squared. So you would have the integral from 0 to 1 of t, or 1 minus t over pi, all divided by sine t, then dt. Now we have to now do integration by part. Point being that, notice that 1 over sine t is the antiderivative, or if you take derivative of logarithm of tan t over 2, you will get 1 over sine t, because if you take this derivative, you will have, first of all, 1 over tan t over 2, and at the top you would have 1 over 2 secant squared t over 2, which means this should equal to 1 over 2. You would have cosine squared t over 2 times sine of t over 2 divided by cosine of t over 2, which will be equal to 1 over 2 sine of t over 2 cosine of t over 2, which will be 1 over sine t, of course, 1 over sine t. So now we know the antiderivative. So let's compute it. This would be equals to 1 over pi squared times the integral from 0 to 1. So sorry, this is pi rather, 0 to pi of t, 1 minus t over pi. Then you will have the derivative of logarithm of tan of t over 2, then all prime, then dt. Now this is now set up, so this will be equal, by integration by part, this should be equal to, you have a 1 over pi squared, then you would have a t, 1 minus t over pi, then you have the logarithm of tan of t over, yes, then you have the logarithm of tan of t over 2. So which we are going to evaluate this part from 0 to pi, and then you have minus 1 over pi squared times the integral from 0 to 1. So if you take derivative of t, you have a 1. Derivative of t squared, you have a minus 2t over pi times what? Times the logarithm of tan of t over 2 dt. Now everything here evaluates to 0, obviously, because you can check it out yourself. Everything there evaluates to 0. So next up, what would have here, you would do, this is equal to, now let's separate it into two integrals. You have, on the first, you have negative 1 over pi squared times the integral from 0 to, of course, pi. Integral from 0 to pi of logarithm of tan of t over 2 plus 2 over pi cubed times the integral from 0 to pi of t logarithm of tan of t over 2, then dt, of course, dt. Next, we are going to make a substitution. Take t over 2 to be x, okay? If you do this, then you would then have dt to be 2 dx. So you would have negative 2 over pi squared times the integral from 0 to pi over 2. The limit as x becomes, as t becomes pi, x becomes pi over 2, and as t becomes 0, x also becomes 0. So you would have here logarithm of tan x and dt. Then on this side you have a 2 plus 2 over pi cubed, then you have 0 to pi over 2, then you have t, so you have a 2x logarithm of tan x, then you have a 2 dx, right? 2 dx. Okay, now this first integral evaluates to 0, and to see that, notice that the integral from 0 to pi over 2 of the logarithm of tan of x is going to equal the integral from 0 to pi over 2 of the logarithm of sine of x minus the logarithm of 0 to pi over 2 of the logarithm of cosine of x. So now dx, of course, dx and dx. Now this first one is equals to negative pi over 2 log 2, and this one is also equals to negative pi over 2. They are equal to each other, and everything becomes 0. That is why everything here evaluates to 0. So we are now left with the negative, we are now left with 8 over pi to the third power times the integral from 0 to pi over 2 of x logarithm of tan of x dx. So this is a much more simpler integral, although it's not so easy to solve, even if it's much more simpler. Next up, the way to approach it is to use the so-called Fourier series for logarithm of tan. And if I remember correctly, this series equal negative 2 times the sum as k runs from 0 to infinity of, okay, I think we have a cosine of 4k plus 2x divided by 2k plus 1. And of course, x is between 0 to pi over 2, is not for all values of x. And of course, our integration is defined from 0 to pi over 2. So we can legitimately plug in the Fourier series. If our integration was from 0 to infinity, we can't use this Fourier series directly without making some change. We have to change the order of the limit of integration from 0 to pi over 2 to possibly 0 to infinity. But this problem is perfectly set up for the use in this interval. So basically this will be 8 over pi cubed, then you have the integral from 0 to pi over 2, then you have an x, then you have a negative 2 times the sum as k runs from 0 to infinity of the cosine of 4k plus 2x all divided by 2k plus 1, then of course dx. Now we can switch summation and raise a negative 16 over pi cubed. Then you would have the integral from 0 to pi over, not integral rather, you have the sum. Okay, so you have the sum here from k runs from 0 to infinity of 1 over 2k plus 1. Then you will have the integral from 0 to pi over 2 of now x times the cosine of 4k plus 2x dx. Now the task is now computing this integral and hopefully computing the sum we get. And this integral, we are going to use integration by parts, of course, and we're going to get negative 16 over pi to the third power times the sum as k runs from 0 to infinity of 1 over 2k plus 1. Then over here you would have an x, then you would yes, you would have an x. Okay, let me just show the full steps involved. What you would have is the sum. No, let's just put the integral first. Integral from 0 to pi over 2. Now you have an x multiplied by cosine of 4k plus 2 odd x all divided by 4k plus 2, prime. Notice that dx. Notice that if you take derivative of this cosine of 4k plus 2x, you divided by 4k plus 2, you will have, no, not even cosine, sorry, sine. If you take derivative of sine of 4k plus 2x divided by 4k plus 2, you would have cosine of 4k plus 2x. So that is the trick for using integration by part. Now we can apply using integration by part. This would be equal to negative 16 over pi to the third power times the sum as k runs from 0 to infinity of 1 over 2k plus 1. Then you have on one part, sorry, you would have on one part x sine of 4k plus 2x all divided by 4k plus 2, and this is from 0 to pi over 2. Then you have minus, then you have the integral from 0 to pi over 2 of sine of 4k plus 2x all divided by 4k plus 2 dx. Now, okay, now this would be equal to, notice that everything here is 0. Everything here goes to 0. So this would be equal to negative 16 over pi to the third power times the sum as k runs from 0 to infinity of, you have 1 over 2k plus 1 times what? Negative times the integral from 0 to pi over 2 of sine of 4k plus 2x all divided by 2 times 2k plus 1 dx. So we can factor out the k terms, and you had negative, you have 8 over pi cubed times the sum as k runs from 0 to infinity of 1 divided by 2k plus 1 to the second power. Then you have the integral from 0 to pi over 2 of now the sine of 4k plus 2x dx. Now all that remains is to just get this sine of 4k plus 2 integral, which is very easy. We can use integration by part, and this will be 8 over pi to the third power times the sum as k runs from 0 to infinity of 1 over 2k plus 1 to the second power. Then you would have negative cosine of 4k plus 2x all divided by 4k plus 2, and we are taking this from 0 to pi over 2. Now if 4k plus 2 is multiplied by pi over 2, you will have a cosine of 2k plus 1 pi, and this will be equals to negative 1. Okay, so you would have an 8 over pi to the third power times the sum as k runs from 0 to infinity of 1 over 2k plus 1 to the second power. Then on one part you have a negative, then you would have a negative over 4k plus 2, then you have a negative 1 minus, now this, if cosine of 0 is actually equals to 1, so you have minus 1 here. So you would have 8 over pi cubed times the sum as k runs from 0 to infinity of 1 over 2k plus 1 square. Then you have a 2 divided by 2 times 2k plus 1. Okay, now this would simplify to 8 over pi to the third power times the sum as k runs from 0 to infinity of 1 over 2k plus 1 to the third power. Now this is known to equal 8 over pi cubed times 1 minus 1 over 2 to the third power times the sum as k runs from 1, yes, k runs from 1 to infinity of 1 over k to the third power. Now the reason for this is because if you have any series, the sum of any series a sub n would equal the sum of the series a sub n when n is even plus the sum of the series when n is odd. Now this is the case where n is odd, so this odd case will be the series a sub n minus the series a sub n for even case, which is why I wrote it as 1 minus 1 minus, so this will be equals to the sum as 1 over k cubed minus the sum as 1 over 2k cubed. So that's why I factored 1 minus 1 over 2 to the third power. That is why I did this. So you would have 8 over pi to the third power, then you would have times 7 over 8 zeta of 3 by definition. So this is basically 7 over pi cubed zeta of 3. So thank you for watching. Please do subscribe to the channel. Bye and have a nice day.